All right, so we're going to get started in just 10 seconds. Trying to trace over some graphs that didn't print out as dark as I would have liked. All right, good morning. I hope you guys are all having an excellent day and an excellent week. Just a couple quick reminders. So your Chapter 1 quiz is due tomorrow, so make sure you log in at some point tomorrow and take that quiz and make sure it gets submitted. It will cover everything through what we covered on Tuesday. There is a review tonight that William is doing from 5 to 6 on sine and cosine. So if you think you need a little extra support in remembering sine and cosine, definitely feel free to stop by that. So today we're going to start chapter 2, and we're going to be talking about limits and continuity. So limits are something that in some calculus courses take up a whole chapter. So, pretty extensive work because it creates a lot of the theory that goes into calculus. We are not going to be doing it quite that extensively, but we are going to talk about just sort of the general characteristics of limits and this idea of what is known as closeness. So we'll be talking about that a lot today. And then when we're in chapter 2, we'll be using some of the processes that we're talking about today for limits to apply to some of the work that we're doing. Okay, so I'm going to go ahead and switch over to the dot cam. Okay. My printer's not working great, so print it out, not how I'd like. So I'm on top of a book today, so if it looks a little weird, that's why. So today we're going to talk about limits and continuity. So the first 2/3 of the class will be talking about limits, and then we'll switch over and we'll talk about continuity because we have to understand limits first before we can then define continuity. Okay, so what is a limit? Okay, so the limit is the dependent value, which we also know is called the output, that a function approaches as the independent variable approaches some value C. Okay, so a lot of our terminology from 1.1 is coming into this definition. So what does this mean? So we are looking for a Y value or dependent value that comes up when we get really, really close to some independent value. Okay, so we're going to start by looking at this visually. We'll do lots of examples on how this works, but the idea is that our independent variable is approaching some number, and when that happens, we want to know, well, what is happening in the dependent axis? What number are we approaching there, if any at all? Okay, and so the mathematical notation for this is the limit as x approaches c of f of x equals L. Okay, so LIM is limit, and then this C, right, that's going to be a number. That's going to be the independent value that we are approaching. And then the L is the dependent value that we are approaching. Okay, so what does this look like? Okay, so let's say we want to do the limit as x approaches 2 of f of x. Okay, so this is a function over here. We're interested in the limit as x approaches 2. So what that means is as we get close to 2, we want to know what we're getting close to in the y direction. And so this is where we start our discussion of closeness. So you can get close to 2 from the left side or the right side. So if we are getting close to 2 from the left-hand side, okay, what we see is that we're moving up the y-axis as we move closer to 2 here, right? If we are getting close to 2 from the right-hand side, so from this side, we can see that we are moving down the y-axis this way. So as we get closer and closer to 2, the y value is getting closer and closer to 4, okay? Now, why am I not saying equals 4? Okay, so when we talk about limits, we're not ever actually plugging in the 2 to our function. We're getting really close to 2. When we talk about getting close to 2, what I want you to imagine is a number line. All right, we're going to put 2 on there. So if 1 is here and 3 is here, 1 and 3 are far away from 2. Okay, so when I say close, I want you to think something like 1.9 or 2.1. That's within 1/10 of 2, or even closer. So something like 1.999. It's a little bit to the left of 2, or 2.001. Okay, so when we talk about getting close to a number in terms of limits or in terms of calculus, we're really talking about being, at least within 1/10 of the number. Even better, 1/1000th within the number. So like really, really teeny tiny close. So what I want you to notice is that we get close to 2, but we never actually use 2. And why is that? Because the benefit of limits is being able to work with functions that may not actually exist or be defined at the value that we are interested in, okay? So we're going to look at a lot of examples, like the beginning one where it does exist, and we say, okay, well, we could have just done it at 2. But the reason we're doing it is so that when it gets more difficult, we have a process to be able to deal with that, okay? So for example, okay, consider the function x squared minus x minus 2 over x minus 2. This particular function, because of this x minus 2 down here, has a hole up here at 2. So if we wanted to talk about the limit as x approaches 2 of our function listed above, right? We could still talk about the limit even though we can't plug in a 2, right? If we plugged in a 2, we get a 0 in the denominator and we're in trouble. But the limit, if we're getting close to 2 from either side, what we see is that the values are getting closer and closer to 3 on the dependent axis. So even though there's a hole there, the limit still exists because we never actually get to 2, okay? So what does that mean we never actually get to 2? Because we're just looking at this visually right now. So we kind of want to figure out what does that mean in terms of calculations, right? How are we going to actually use these close numbers? So there's one more thing we have to consider, and then we'll be able to start looking at practicing in a way that highlights this, okay? So the last definition we need to talk about before we can sort of jump in is this idea that when we approach a number, we can approach it from either side, right? So we drew those arrows both to the left and the right. So we need a way to talk about which direction we are considering, because when we do this more formally with algebra, we do have to plug in numbers literally to the left and the right. And so we want to have notation for that. So when we are picking numbers that are slightly bigger than the number we are interested in, we are taking a limit from the right. And what we do is we use notation which is this plus sign. And this plus sign indicates that we are approaching our value from the right and something slightly bigger than the value we're looking at. So for 2, that might be 2.1, 2.01, right? Something slightly bigger than 2. We're approaching it from the right-hand side on a number line. If we're approaching it from the left, we use a minus sign up in the exponent here to indicate that we have something slightly smaller than the number we're looking at. Okay, so when we find the value from the right, we use this notation with the plus. When we look for it from the left, we use notation with this little minus. Okay, and hopefully this will make sense once we do an example here. So we are going to start with an example that hopefully won't be too complicated computationally because we're trying to get used to the process in this one. So I'm just going to write this a little bit bigger. So the limit as x goes to 3 of 9 plus x, right? So we're asking the question, what y value are we going to approach as x approaches 3 for the function 9 plus x? So you probably have a pretty good idea of what it's going to be before we do any work. But again, this is about the process. So what we're going to do is we're going to take numbers slightly less than 3. So 2.9, 2.99, 2.999. And we're going to use that to determine the limit as x approaches 3 from the left of 9 plus x. So this is the left-hand approximation. So we take each of these numbers that are slightly less than 3 and getting closer and closer to 3, and we plug them into the function that we're looking at. And we get the outputs, and we're asking what do they approach. So we're looking for a pattern to determine what value they're approaching. We are also going to look at the limit as x approaches 3 from the right. Okay, so that means we're using numbers slightly bigger than 3, 3.1, 3.01, 3.001. And we're going to plug those into 9 plus x and see what those dependent values are approaching. Okay, so I want you to take 2 minutes, okay, plug each of these values into the function and fill them in next to them in a chart. The idea is to see what they're approaching as we get closer and closer to 3. So these numbers demonstrate that we are getting closer and closer as you move down this column, okay? And then you're gonna do the same thing with these values, and then hopefully you'll be able to see what the dependent values are approaching. So take 2 minutes, fill that out, see what comes up, see if it's what you expected, and then we'll go through it together. Okay, take about 30 more seconds. All right. So when we plug these values in, we plug 2.9 in and we get 11.9. We plug in 2.99, we get 11.99. We plug in 2.999, we get 11.999. And this is where we take our critical thinking and our mathematician hats and we say, okay, This is approaching 12 because every time I get a little bit closer, I add another 9, which is getting me a little bit closer to the value of 12. Okay. When we do the same thing over here, we're going to get 12.1, 12.01, 12.001. So again, we see that as we get closer and closer to 3, this decimal is getting smaller and smaller. So this is also approaching 12. Okay, so here is now something that we need to learn a little bit more about limits. So here, the limit from the left exists and is 12. The limit from the right exists and is 12. If the limit from the left is the same as the limit from the right, that's when we can say the limit as x approaches 3 of 9 plus x equals 12. So we can say that the whole limit with no qualifier equals 12 as long as the left and the right are the same. If the left and the right were different, we would say that this limit does not exist. Okay, we will get to some examples of that in a little bit. Okay, so again, you may have looked at this and said, okay, but you can just plug in a 3 and see that it's 12. Well, yes, because this particular function is not as complicated as some of the ones we want to approach, but with limits, we never actually plug in a 3, right? We plug in things around it, but we're never plugging in the 3. If you have a good idea of what the limit is going to be, because you look at something like this, that's great. That's going to give you a map to make sure that the work you're doing is aligning with what you think the answer should be. So let's look at an example now where it may not be as obvious what this limit is going to turn out to be. So here we're talking about the function, I'm going to write this a little bit bigger. The limit as x goes to 0 of the natural log of 2 plus x minus the natural log of 2, all divided by x. Okay, so you may not know what the limit is as x goes to 0, because if you just tried to plug in 0, you get 0 over 0. And whenever you have 0 over 0, that means you have something that you don't know what it is. It's an undetermined form. Okay, that doesn't mean it's 0 or infinity. It just means that we don't have any information and we need to do something else. So what we're going to do is we're going to look at the limit from the left and the right and see if they exist and if they're the same. So here, we're going to do the limit from the right by plugging in things like 0.1, 0.01, 0.001. And then we're also going to do it from the left. I'm going to hold this. Right, so we're also going to do the limit from the left by doing negative 0.1, negative 0.01, and negative 0.001. Okay, so what you need to do for each of these values is plug it into this function and see what the dependent value is. So be really careful with the parentheses and the division here. And then you're trying to determine if this is approaching some particular value. If the left and the right are approaching the same value, then the full limit will go to that value. If they're approaching different values, then the limit does not exist. Okay, so I'm going to give you 2.5 minutes to plug these in. Try to be really careful with the parentheses again, but see what you can figure out here about what these are approaching. Okay, so take that time and then we will go through it together. Okay, take about 30 more seconds. All right. So when I plug in 0.1, I'm going to recommend that you typically keep like either 3 or 4 decimals when you're plugging in different things, just because that will help you sort of know how far the decimal is accurate, if that makes sense. So for 0.1, I got 0.4879. For 0.01, I got 0.4988. And for the last one, I got 0.4990. Okay, so what I notice here is that these are getting closer and closer to 0.5. Okay, so I'm making that leap from what I'm seeing here. This is pretty small. If I wanted to be sure, I could certainly check 0.0001. You can always add more zeros. But the further you go closer to 0, the more accurate you are. So I'm going to say that this limit is 0.5. So now when I do this from the other side, when I'm approaching from the left, I'm going to plug in negative 0.1. I get 0.5129. And then I'm going to get 0.5013. And then finally, I get 0.5001. So what I see is, again, I'm approaching 0.5. These decimals are getting smaller and smaller as I get closer and closer to 0. And I'm in luck here because my limit from the left is the same as my limit from the right, which means that my final limit is also 0.5. Okay, so the last 2 examples we looked at is how we would approach this algebraically. Okay, and what we see is that in both instances, the limits exist and they are the same. That's pretty common for algebraic functions. Occasionally, you'll have one that as you do the numbers, you see they're blowing up to infinity. That's when they do not exist, but that's pretty uncommon. Okay, so now let's do some considerations of what things might look like when they don't exist and how we might recognize them. So the next example we're going to look at is this graph below. And from this graph, we are interested in the following limits. The limit as x goes to 1 of f of x, the limit as x goes to -1, the limit as x goes to 2. So in order to think about these and to sort of put into practice what we've been doing, what we need to do is find what's happening from the left and the right for each of these limits. So we want to find the limit as x approaches 1 from the right. We want to find the limit as x approaches 1 from the left from this picture. And then if they are the same, then that is the limit as x approaches 1. And if they are different, then the limit does not exist. Then we're going to do the same thing for -1. So the limit as x approaches -1 from, we'll do the right first, and then the left. Okay, the order doesn't matter if you do left or right first in your own work. Just trying to be consistent. And then when we consider what's happening at -1, if the left and the right are the same, then this one exists. If they are not, it does not exist. And then the limit as x approaches 2 from the right, and the limit as x approaches 2 from the left. And then again, we'll use that to make a final determination for this one here. Okay, so hopefully you can see sort of where all these things are marked. I tried to darken them up, but we're counting by ones in both directions. So once you take about 2 minutes, see if you can figure out what these limits are going to be, the left and the right, and then use those to talk about the general limit. Okay, so take about 2 minutes and then we will go through it together. Okay, take about 30 more seconds. All right, so let's start with the limit as x approaches 1 from the right. That means we're approaching 1 from something slightly bigger than 1. So that means we are up here. Okay, we're on this part of the function because we are slightly bigger than 1, moving towards 1, and we never actually reach 1. We just get really close to it. So the dependent value that I see approaching here is 3. Okay. When we approach 1 from the left, we are down here on this part of the function, right? And we're coming up towards 1 from the left. And so that is approaching 1. So what I notice is that these are different. So the limit from the left does not equal the limit from the right. So the general limit, we say, does not exist. And we will often notate that DNE. Okay. So in terms of clarity and terminology, the limit from the right exists and is 3. The limit from the left exists and is 1. But the limit as x goes to 1 does not exist because the limit from the left and the right are different. Okay, so these both exist just fine, but this one does not exist because these are different. Okay, so now let's consider what's happening for -1. So for -1, when we approach from the right, we are starting a little bit to the right of -1. So we are coming up this way, right, on the track. And as we get closer and closer to -1, the y value is getting closer and closer to 1. And then when we approach from the left, we're coming down, right, because we're on this side of 1. So we're coming down this way to get closer and closer to -1. And as we do that, we see this is also approaching 1. So the limit from the left and the limit from the right are the same, which means that the limit as x approaches -1 is 1. It's also that value because they are the same. So in this case, the limit from the right exists and is 1. The limit from the left exists and is 1. And so the general limit as x approaches -1 is also 1. Okay. So then we look at what's happening at 2. So when we approach 2 from the right, we're somewhere over here between 2 and 3. So that means we are on this part of the function coming down. Okay. And what I see is that's approaching an x value of 2. When I approach from the left, I notice that I'm on this part of the function up here, going this way. So again, the dependent value is 3. And so again, I see that the left and the right are not the same. So my general limit does not exist. Okay. So those are the cases where does not exist typically comes up. So you really do need to look at what's happening from both the left and the right to figure out if it exists. Now, visually, you can kind of see where these issues are going to come up because we have these jumps, right, that are in different functions. So you have a pretty good sense of where they're going to be, but sometimes you are asked to find the values to then showcase that they are different. Okay. Now, one other thing that I wanted to show you is that when you are doing limits algebraically, like we were to the examples prior to this, one thing that you can do is you can simplify algebraically before you do the limit. You do not have to. This is an option. So I'm just going to write this a little bit bigger. So the limit as h goes to 0 of 2 plus h squared minus 4 over h. Okay, so this is the function we're looking at. Now, a couple things. One, you could do this limit as we did before without simplification. So you would create your table, which we're going to do anyway, and you would have values like 0.1, 0.01, 0.001, right? That's getting closer to 0 from one side, and then -0.1, -0.01, -0.001. And you could plug them in for h and create that chart with the dependent values. However, you are also able to simplify algebraically first. And so that's what we're going to try here. And the benefit of doing that is that when you go to plug in those values later, it's just easier to plug them in so you don't make a mistake. Okay. So what I would like you to try to do, okay, is I would like you to try to algebraically simplify this first and then plug in values. But again, with the caveat that if your algebra is not as strong or you're worried about this, you can just plug into this without having to do that. But I want you to see that option. So what does that look like? I want you to factor this out. I want you to simplify any like terms, cancel out anything that makes sense. And then once you've done that, you can go ahead and create the chart, right, where we're doing 0.1, 0.01, 0.001, into whatever your simplified function is. And then also -0.1, -0.01, -0.001, and see if the limit from the left and the right are the same, right? And then we'll know if the full limit exists, okay? So I'm going to give you about 2.5 to 3 minutes. Again, first, I want you to try to think about this algebraically. It's good practice because we will be doing this type of algebra later in chapter 2 without limits in sort of a different context. So practicing now is a good idea. Okay, so take 2.5 minutes, simplify this, then do the limit, see what comes up, and then we'll go through it together. Okay, take about 30 more seconds. All right. So to begin algebraically simplifying this, the first step is to FOIL out the 2 plus h. When you do that, you're going to get 4 plus 4h plus h squared. And then we still have the minus 4 and divided by h. So combining like terms, we see that we have a 4 and we have a minus 4. So those are going to cancel. Okay. And those are going to leave us with the limit as h goes to 0 of 4h plus h squared over h. Now, hopefully you notice that everything has an h in it, because the next step here is to factor out an h. Whoops, we're going to come down this side. So we have h times 4 plus h over h. Okay, by factoring out that h, now we can cancel it. So we're finally left with the limit as h goes to 0 of 4 plus h. So the goal in simplification is now when we plug in values closer and closer to 0, they're much easier to plug in to the function, right? And we have a pretty good sense of what the limit is going to be by sort of eyeballing it. So we're plugging it into 4 plus h. And again, if you didn't get this far, say you got here, you can still apply this here and you will get the same answer. It's just more likely that you might make a small calculator error. So don't feel like if you didn't get all the way that you've messed something up, because you can plug in here, you can plug in here, you can plug in here. The goal is just that this is slightly easier to plug into. So when we plug in stuff from the right, we have 4 plus 0.1, so we have 4.1, then we have 4.01, 4.001. And what we see is that these values, the decimals are getting smaller and smaller. So this is getting closer to 4. Okay, so we have the limit as h approaches 0 from the right of our function equals 4. This is f of h, right? If we do something similar from the left, we have negative 0.1, which is going to give us 3.9, negative 0.01, so 3.99, then 3.999. So again, we see is that we get closer to 0. This is getting closer and closer to 4. So we have the limit as h goes to 0 from the left of f of h also equals 4. So since it's the same from the left and the right, what that tells me is that the full function as h goes to 0 also has to be 4. Okay, so again, the idea here is just to showcase that you can algebraically simplify before you do the limit, if that is a preference of yours. Okay, so one final sort of look at limits before we switch over to continuity. I'm going to give you a picture here. And what I want you to do is I want you to think about where this function has limits that exist and where they don't exist, and more focus on where on this function is the limit not going to exist. Okay, so I'm asking you to eyeball it. Just think through what we've talked about in terms of definitions. You know, left and right have to be the same, and see if you can identify the places where this will not exist. You don't have to write out a ton of stuff. I just want you to sort of eyeball it and come up with where you think it'll be, just a couple of guesses. I'll give you about 30 seconds to really look at it, and then we'll go through it. Okay, so hopefully what you notice is that at 1, we kind of have these jumps, right? That the limit from the left is different from the limit from the right. So we can say the limit as x approaches 1 for our function does not exist. So that's one of the places where it's not going to exist, because again, we have these jumps which cause the limits from the left and the right to be different. That also happens over here at -1. So at -1, the limit from the left is just about 0, and the limit from the right looks like it's about 1. So again, the limit as x goes to -1 does not exist. So these are the two places on this graph where we can see that the limit's not going to exist. We don't really know what happens outside of the graphs, right, over here, so we're not worried about that. But for every other value, when you approach it from the left or the right, every other x value, it approaches the same thing from the left and the right. So everywhere else that we can see, the limit does exist. But in these places where we have these weird jumps, that's where it doesn't exist. Okay. Now we're going to shift and talk about continuity. But as I mentioned, the definition for continuity, which we're going to talk about in a second, relies on limits, right? So that's sort of how this ties in. And so I want to talk about continuity in general with the definition and then in practice, I suppose. So let's start with just what continuity is. So a function is said to be continuous, so that's the word we use, if there are no holes or no breaks, jumps, or holes on the interval being considered. Okay, so if you've talked about continuous functions before, you may have heard like a continuous function is a function you can draw without lifting your pencil off the paper. That's a good way to think about it, right? That means that there's no jumps or holes or breaks. It's a little more technical than that, but that's just sort of a good kind of coverall reference that mostly works. Okay, now I really want to talk about this idea of the interval being considered. So if we look up here, we can see that there's breaks at 1 and -1. So we're not going to be continuous there because it violates this idea. But if I asked you if this function was continuous between -2 and -3, the answer would be yes, right? Because that little patch doesn't have any of those issues, right? From -2 to -3. So if you are given an interval to consider, make sure that you are just looking at that interval, because I could give you this whole picture and ask you, is this function continuous between -2 and 3? And the answer is yes, right? But if you just look at it quickly and think that we're talking about the entire picture, then you would say no because of these. So make sure that you know where you are looking when you're talking about the continuity, okay? Now, I would say about 20% of the time you're going to have an interval. The other 80% you won't, and we'll talk about why in a few minutes. But keep in mind it does show up sometimes, so just be sort of aware. Now, the definition, the mathematical definition of continuity is a function f of x is continuous at x equals c. So we're talking about a very particular point, some value, if f of x is defined at x equals c. So that means you can actually plug in the x value with no issues. And the limit as x goes to c of f of x equals f of c. So not only is the function defined at that point, the limit also is that value. Okay, now you may think that this is always true, but it is not. If you look at the picture above, right, f of 1 in this picture is -2. The limit as x approaches 1 from the right, is +2. The limit as x approaches 1 from the left is 1. So these are all different. So this is not continuous at 1, right? So not only do we need the function to be defined at that point, we need the limit to be the same as the output you're getting when you plug it in. Now, we're going to do one example and go through the definition so you can see how it works. And then we'll sort of talk about alternatives to how we might think about continuity. So here we are considering the function x squared, 3x squared. And we want to show using the definition that the function is continuous at 1. So how do we do that? We have to show the functional value. So we need to find f of 1. And then we need to determine the limit as x goes to 1 for this function. How do we determine the limit? We do the limit from the left and the right of 1. So we're using things like 0.9, 0.99, 0.999, 1.1, 1.01, 1.001. So if we can show that the limit's the same from the left and the right, then we can show that the limit exists. And then we're hoping it's the same as what we get when we plug a 1 into the function. Okay, so I want you to try to do out all these steps. I know it's sort of a lot all at once, but see what you can do. I'm going to give you 2.5 to 3 minutes. But again, you want to find the limit as x goes to 1 for 3x squared, the same way we've been practicing all of class. And then the additional step is to find f of 1 by plugging 1 into the function. Okay, so take 3 minutes. Then we'll go through it together. Feel free to work with someone next to you or ask a TA if you're a little bit confused about the steps, but then we will go through it together. Okay, take about 30 more seconds. All right, so let's check all the things we need to check here. So first we need to, or not first, but one of the things we need to find is f of 1, which is the functional value. If we plug in a 1 here, we have 3 times 1 squared, which is 3. Okay, you don't have to do that first. That's just one of the things. Now, to figure out the limit as x approaches 1, we need to look at the left and the right to make sure they're approaching the same thing. So when we plug in to 3x squared, when we plug in 0.9, we get 2.43, 0.99, we get 2.9403, 0.999, we get 2.994. So what I'm seeing here is I'm getting more nines as I get closer and closer to 1. So I'm pretty confident that from the left, I am approaching 3. Similarly, I need to see what's happening from the right. So I plug in a 1.1, which is 3.63. 1.01 is 3.0603. And 1.001 is 3.006. So again, what I'm noticing is my decimals are getting smaller and smaller. So that is also approaching 3. So that means my limit as x approaches 1 of 3x squared is 3, because it's the same from the left and the right. And since the limit is the same as the functional value, my function is continuous at x equals 1. Okay, so if we want to determine if something is continuous at a particular point, then this is what we need to do. We need to look at the functional value and the limit. We evaluate the limit by looking at the left and the right. Now, this is one of the ways we look at continuity, but not the most common way. I will say that this is sort of the process maybe 10% of the time. And more commonly, when thinking about continuity, we are actually linking back to domain, okay? And so what does that mean? So I'm going to go ahead and I'm going to skip down to this paragraph for a minute, and then we'll go back and look at the next set of examples. But there's several types of functions that are continuous wherever they are defined, okay? So when we talk about something being defined, we're talking about the domain of the function. And those are polynomials, so your x squareds, x cubes, rational functions, which is the ratio of polynomials, exponentials, so 5 to the x, e to the x, anything like that, sine and cosine, also natural log of x, which I forgot to write in here. Additionally, functions that are created by adding, multiplying, or composing these functions are also going to be continuous wherever they are defined. So what does that mean? So let's take the example of the natural log of x, okay? So the domain for the natural log of x is that x has to be positive, okay? The natural log does not exist for negative numbers or 0, so the domain is x is greater than 0. So what that tells me is the natural log of x is continuous for x greater than 0, because that's where it's defined, that's its domain, okay? So oftentimes we're going to look at a function and say, where is it continuous? Where is it not continuous? Sort of a good example question that could come up on a quiz or something like this would be, which of the following functions is continuous from -1 to 1, right? And so we're asking, can you plug in all of the values between -1 to 1 for some particular function? So for the natural log of x, the answer would be no, right? Because we can't plug in a -1. But for x squared, the answer would be yes. You can plug in all the values between -1 and 1. So you really have to compare your interval to the domain, okay, for a lot of functions. That's how I want you to think about it when you're just given some function and asked, where is this continuous or where is this not continuous? You need to think, what is the domain of this function? Okay, so in keeping that in mind, let's go back to example 2 here. Determine where the function f of x equals 2 divided by x over 4. I'm going to write this a little bit bigger here. Determine where this is not continuous, okay? So I want you to take 1 minute. I want you to look at this. I want you to think about this. I want you to ask yourself, what is the domain of this function? Because the domain is going to help us figure out the continuity. And then I want you to think about how we learn to write down with either interval notation or otherwise where this function is continuous. Okay, so there's sort of 2 steps: figuring out the domain so we can figure out the continuity, and then figuring out how do we write that down, what is the right notation. Okay, so take 1 minute, see if you can figure it out. Okay. So hopefully some sort of warning bells went off for you about x equals 4, right? So we do have a denominator in this case. So this is a rational function, so a polynomial over a polynomial. These are both polynomial terms. And so x equals 4 is not in the domain for this function, right? You can plug in whatever you want except for 4. So there's two different ways that we can state this. We can say x cannot equal 4. If you say that x cannot equal a value, the implication is that it could equal anything else, which is what we're trying to come across here. Or we can use interval notation like this. So x is an element of negative infinity to 4, open brackets, because we're not going to include 4, and 4 to infinity. Right? So this is everything but 4. These open brackets are going to be what takes 4 out of the running. So either one of those could represent where this is not continuous, because again, this is based on where it's defined. Okay. So the next one, I want you to see if you can think about this. Determine where the following function is continuous. So this is a piecewise function. So this is x squared minus 4. We'll write that a little bit bigger. X squared minus 4 for x less than 0, and x minus 4 for x greater than or equal to 0. Okay, so I want you to take a minute and think about, is it continuous everywhere? Is there a place where it's not continuous? And if there's a place where it's not continuous, why wouldn't it be continuous there? Okay, so take 1 minute, think it out. You can draw those pictures if you need to, but see if you can figure out what the situation of continuity is here. Okay, so if we look at each of these functions individually, x squared minus 4 doesn't have any big issues, right? X squared minus 4 is continuous everywhere. So as an individual function, there's nothing we're worried about. Same thing with x minus 4. If we just think about x minus 4, we can plug in whatever we want into x minus 4, and there's no big issues. So individually, both of these functions are fine. The other question that comes up is what happens at 0, right? Because this is where we change functions. And when we have a piecewise function, we could end up with a jump here, right? Depending on how it's defined. So what we need to consider is what is the value of each of these functions when x equals 0, okay? Because we're essentially taking the limit to see if it's the same, to see if a jump was created or if these overlap smoothly. So if we plug a 0 into the bottom function, right, which is where it equals 0, we have x minus 4, which is negative 4. But then we also want to consider what value is this approaching in terms of a limit, since we don't have the equality here. So the limit as x approaches 0 from the left of x squared minus 4. So as you get closer and closer to 0, you will see that this also approaches negative 4. So since it's the same at the point where it splits, and since neither of these have any individual problems with domain, that means this function is continuous everywhere. Okay. If you are not 100% convinced, I would say you should go ahead and graph this, and you will see that you can draw it without lifting your pencil up. Okay, so that's how we would approach it. We'd look at each function individually to see if there's any issues and note those. And then we also consider what happens at the point where we're splitting up the function to see if there's any jumps. Okay. All right, so let's look at one more example here on continuity. So Consider a pay by the hour parking garage. Any fraction of the first hour is $8. So you pull in, $8. At the 1 hour and 1 minute mark, the price jumps to $16 for the second hour. Okay, so once you go over the 1 hour mark, it jumps to $16. Okay, and it's $16 for the entire second hour. So 61 to 120 minutes. Then again, it jumps up another $8. So 24 hours or $24 for hour 3, right? So on and so forth. So every new hour slot, you get charged another $8. So what I would like you to do is I would like you to try to draw a picture of what this might look like, roughly, okay? And then discuss from that picture, what is the continuity of this function? So where is it continuous? Where is it not continuous? I want you to think about what the picture would look like. I want you to label the axes, okay? And then I'm going to give you, I don't know, 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so when we set up our picture, okay, the dependent output here is the cost, right? That's what's changing based on time. And then the independent axis should be time. There's 2 ways that you can set up this picture. You can do it in minutes or hours. It's going to be roughly the same. Either is totally fine. So here, we'll put 60, and then we'll put 61, and then 120, 121, right? 180, 181, right? So you can do it that way. You could do like 1 hour, 2 hours, 3 hours. It means the same thing. There are no explicit instructions on the variable, so either is totally fine. So what's happening during the first hour, right? So during the first hour, up to and including 60 minutes, right? We are getting charged $8. But right at 61 minutes is when we make our jump, right? So 1 minute after the hour mark, we make our jump up to $16. And then we stay at $16 up until 1 minute past the 2 hour mark. And then we make a jump up to $24, right? And so we can kind of predict that it's just going to keep doing the same thing as we add on time, okay? So the main thing that I'm hoping that you found in your picture is that we have this like step function, that we're going to have this jump to a new price, every roughly 1 hour. And so that jump, those points where we jump, is not continuous. Okay. But everywhere else it is. So if we're talking about minutes 30 to 45, if you stay from 30 to 45 minutes, that part of the function is continuous, right? You can draw that without any issues. Where we have these issues is where we change over into the next hour, right? So it's whenever we jump up into the new hour band. So this happens at 61 minutes, 121 minutes, 181 minutes, right? And so we can kind of predict by looking at multiples of 60, and then you go one more, that's when we're not going to be continuous. That's when that jump is going to happen. So again, when we talk about continuity, it's not always simply a matter of, is this function continuous or not? We would say, no, it's not, right? Because we have these jumps. But we could also be more nuanced and say, well, the function's continuous except for 1 minute after every hour, right? At those points is where we have those jumps. And sometimes those jumps mean something in some sort of real world context. So being able to identify when the function is not continuous can be really helpful sometimes. Okay, so hopefully you were able to get a good visual representation of that on your picture. That is the last example we're going to do for today. So good luck preparing for the Chapter 1 quiz tomorrow, and I hope you guys have a nice weekend, and I will see you all on Tuesday.